Welcome to the live problem solving sessions for the course on traffic engineering. I'm Sethi Vinayagam, PhD scholar in the Department of Civil Engineering at IIT Madras. Okay, let's start today's session by recalling what was taught in the lectures for week 12. Okay, so this week we were focused on road safety, right? So we looked at 5 different lectures on first how to represent the crash data and analyze it. Then we also looked into road safety audit, which was introduced in the last week. And then we looked at 3 different approaches or measures, which is so safe system approach, road safety countermeasures, and speed management measures. Okay, so in the first lecture, so we were looking at how to analyze the crash data, right? Last week we were looking at parking data, right? How to represent and analyze the parking data. Here we were focusing on crash data, right? So crash data means data from crash incidents taking place on the roads. Okay. So first, with respect to how representation of this data, how do we represent the data that we collect, right? So there are different parameters which we use to represent the number of crashes. Okay, for the first one, so we look at crash rate. Okay, so crash rate, again we can use different parameters or different formula for representing the crash rate. Okay, so one way of doing it is number of crashes per kilometer. Okay, so number of crashes that takes place in 1 kilometer of the road. So we can use that as the crash rate. So other way of representing the crash rate is number of crashes per million vehicles. So this is the rate with respect to the number of vehicles that are traveling. Okay, so this is more useful for intersections when we are analyzing intersections. So where the number of vehicles that are passing through the intersection can be used for deriving the crash rate. And yet another way of representing the crash rate is in terms of vehicle miles travel, in terms of the distance travel. So number of crashes per million vehicle kilometers. Okay, so here we are taking the crash rate uh, per distance travel, right? So total distance travel, right? So here we are counting all the vehicle kilometers for a given segment of the road, and then we are taking and looking at the frequency of crashes per per million vehicle kilometer that is travel. Okay, so here as more and more vehicle travel happens, so higher number of crashes are expected, right? So these are the 3 different ways in which the crash rate itself can be represented. And then the second way is to represent is to look at traffic exposure. So traffic exposure is basically how many vehicles are exposed to potential accidents, right? So here basically we are counting the number of vehicles that are using the road segment. Okay, so so again 2 ways in which we can express traffic exposure. So one is total number of vehicles entering a location during a given period. So this is basically like counting the flow, right? So the spot that we are analyzing, so we are counting how many vehicles are passing through the spot in a given duration, right? So our analysis duration. So that is, so all these vehicles are exposed to the traffic conditions. Second is to look at vehicle the total distance travel, right? So exposure can also be expressed in terms of total vehicle kilometers traveled over a section in a given period. Okay, basically, if you take a section of length L, right, and if n vehicles, number of vehicles that are crossing are passing through the section is n, then what is the total vehicle kilometers travel? It would be nothing but n into L, right? So this is the total vehicle kilometers that is traveled over that section or for a given period of time. Okay, so we can represent the traffic exposure in these two ways. So to obtain the crash rate, now what we can do is, so we can take number of crashes and divide it by exposure, right? So this becomes a generic formula for all the three different ways in which we can express the um, crash rate, because exposure can take different forms, right? So if exposure is total number of vehicles entering during a given period, so then that would become this part, right? So the crashes, number of crashes per million vehicles, that can be derived. If exposure is expressed in terms of total vehicle kilometers traveled, then we will obtain number of crashes per million vehicle kilometers if we express exposure in terms of million vehicle kilometers, right? So these are the ways in which the crash data can be represented. So some more ways in which we can do it are crash involvement rate. Right, so what is crash involvement rate? So here we look at, instead of number of vehicles, we look at number of drivers with a given characteristics who are involved in crashes per 100 million vehicle kilometers of travel, right? So this is number of drivers involved in crashes divided by uh, number of 100 million vehicle kilometers travel, right? So in terms of distance traveled and number of drivers who are involved in the crashes. So that is crash involvement rate. How many drivers are getting uh, involved in crashes? And then we also have death rate. Okay, so this is 3, this is 4. Okay, so death rate is basically how hazardous is a particular community is, right? So here we look at the number of traffic deaths that happen in a year divided by the total population of an area. Okay, so here we are looking at how hazardous or how vulnerable is a particular population in a given area, right? So this is for a area. The previous ones that we were looking at is for a certain spot or a segment, but here we are looking at the traffic hazard for a particular population in an area. Okay, so that's what was taught in the crash data representation. So once we have collected this data and we have derived these different measures, okay, so we got a basic idea of what the data represents. So then we go with the crash data modeling. Okay, so for crash data modeling, so there are two major ways. Are two major methods that we use. Okay, so one is the statistical models, another one is the machine learning models. Okay, so under statistical models, so again we have two types. So depending on the data that we are using. So if we are using like if we are using the crash count, that is the frequency data, then we go with a certain set of models. And if we go with crash severity models, crash severity data, then we go with another set of models. Okay, for crash count, so crash count is basically a continuous numerical variable, right? So here the models that are more appropriate for modeling such kind of data are Poisson regression models like Poisson regression, negative binomial regression. Okay, so these kind of models are more suitable for modeling data count data, right? So count data means we have integer outcomes. Okay, so crash frequencies are integer outcomes, right? One crash, two crash, three crash, and so on. So for such kind of data, the Poisson regression or negative binomial regression. So such kind of regression models are more appropriate. Whereas in crash severity, what are we modeling? We are modeling the severity of the crash, which is like fatal crash, major injury crash, minor injury crash, or no injury crash, right? So here the outcome is a qualitative variable, right? So it's not a number; it's only a category, right? And but within this, among these categories, there is an inherent ordering present, right? So in terms of the severity, fatal crashes are the most severe one. Then comes the major injuries, then minor injuries, finally no injury crashes, right? So there is an inherent ordering among these categories. So we go for ordered models such as ordered logit, ordered probit, right? So such kind of models are more suitable for modeling the crash severity type of data. Okay. Then we have another kind of modeling approach, which is using the machine learning model. So machine learning is basically a subset of the artificial intelligence, right? So here we use the machine learning algorithms, right? So that the machine can learn from existing data and which is used to predict for newer scenarios or observations. Okay, so again, within machine learning, so we have different types depending on what kind of data that we are having. So one is supervised learning methods, then we have semi-supervised methods, and finally we have unsupervised methods. Okay, so where do we use supervised learning methods? So when we have labeled data. So labeled data means where the outcomes are known, right? So where the outcomes for each observation is known. Like for here we are looking at crash data modeling, right? So the crash counts, if you know the crash counts for a particular site, or the crash severity of all the crashes present in our database. If you know those outcomes, then that means that we have a label data, right? So for label data, supervised learning is appropriate, right? The semi-supervised is in between supervised and unsupervised learning. So where we have some labeled data and lots of unlabeled data, right? So for some of the crashes, you know the crash severity, but for most of the crashes, you know that a crash has happened, but you do not know the crash severity, right? So that particular information is missing from your data. So if you have such kind of data, then you can go with semi-supervised learning methods. And finally, we have unsupervised learning. So this is suitable where you have unlabeled data, right? So you do not know the outcomes, right? So the outcomes are not recorded, only the characteristics of the crashes are known, right? So like at what time the crash happened, which vehicles were involved, like such kind of information is known, but what is the outcome, what happened in the end, like was it a fatal crash or not? So such kind of information is not known, right? So which means we have unlabeled data. So for such in such scenarios, you go for unsupervised methods. Okay, so these are the different ways in which we can model the crash data. Okay, and then once we go with once we have picked our models, right? So we build the model. How do we measure how well it is performing, right? So for evaluation, we have different performance metrics, right? So here mostly we are dealing with qualitative scales of the different variable, right? So whether like the crash severity. So in that case, some of the appropriate measures are accuracy, precision, recall, then we have specificity, um, and then we have the F score or the F measure. Okay, so to define these performance metrics, so we have to know four terms: true positives, true negatives, false positives and false negatives. Okay, so if we take an example of a binary decision model, right, like we have to predict whether true or false. Okay, each observation's outcome belongs to one of these two classes, right? So true or false. So in that case, so true positive means the model's prediction. Okay, let's say what is the actual outcome and what is the predicted outcome. Okay, so the actual outcome is true. Okay, and the model also predicted the outcome is true for this for that observation. Then we say it is a true positive. Okay, and true negative means the actual class for that observation is false and the predicted outcome is also false, right? So in that case, it is a true negative. False positive means actually the observation belongs to the false class, but the model has predicted it to be a true class. Okay, in this case, the prediction is a false, is falsely saying that it is a true observation, right? So it is a false positive, and false negative is in reality, the observation belongs to the true class, but the model predicts that this observation belongs to the false class. Okay, so this is a false negative. So in terms of this true positive, true negative, false positive, and false negative. So accuracy. So if we say this is A, precision is P, recall is R, specificity is S, and F measure of F score is F. Then accuracy is what? Accuracy is out of the total sample size, how many of the observations have been correctly predicted, right? So whether they are true or false, irrespective of that, how many are correctly classified. So that is your accuracy. So true positives plus true negatives, right? So this is all the observations which are correctly predicted by the model, right? So true positives and true negatives where the actual is matching the predicted. Okay, so out of all the observations in the model, true positives plus true negatives plus false positives plus false negative, so this is nothing but your sample size. This is the total number of observations, right? So every observation belongs to one of these four categories, right? So it could be either a true positive, true negative, false positive, or false negative. So sum of all those will be equal to a sample size. So accuracy is how many observations are correctly classified in the complete sample size. So next we have precision. In precision, we look we look at a subset of our samples. Okay, so which is true positives plus false negative, right? So true positive means the actual is also positive, predicted is positive. False negative means actual is positive but predicted is negative, right? So which means that this is equal to all true observations. Okay, so all the observations where the outcome is true, right? So where the actual outcome is true, so those observations, among those observations, how many have been correctly classified? So all the true positives. Okay, so all the true positives among the all the true observations. So that is your, sorry, this is not precision, this is the recall. Okay, so precision is again how many true positives out of all the true predicted observations, right? So this is all true observation, this is all true predictions. Okay, so among all the predictions where true was the prediction, so we look at how many of them are correctly predicted, right? So that is precision. So F score is basically a combination of your recall and precision. Okay, so basically it will be the harmonic mean of the recall and precision. So it will be 2 times precision times recall by precision plus recall. Okay, so that is your F measure, and we have specificity. Specificity is like your recall, but it is for the negative observations, right? So recall was for the positive observations. Specificity is similarly for the negative observation. So among all the negative actual observations in your sample, how many are correctly classified? Okay, so that gives you a specificity. Okay, so these are the different commonly used measures for evaluating the performance of the crash data models. Okay, so that's all that was covered in the first lecture. Okay, the second lecture we were looking at RSA stands for road safety audit. Okay, so this we were introduced to this concept in the previous week. Okay, here we were looking at it in a detailed manner. Okay, so what is road safety audit? So road safety audit is basically a it's a formal procedure. What is this procedure for? This procedure is for conducting assessment of road infrastructure with respect to the accident potential and the safety performance, right? So we are making an assessment of roads. This could be existing roads or roads that are planned to be built, or any project which interacts with road or road users. Okay, so it's a procedure for assessing these kind of infrastructure for how what is the potential for accidents to occur on these infrastructure, and how performant is it with respect to safety features. Okay, so that's what happens in a road safety audit. Okay, so we are trying to quantify or estimate the potential for road safety issues, and also come up with opportunities or solutions for mitigating these issues. Okay, so that's the road safety audit. So there are different stages that are present in a road safety audit. So there are 6 different stages, right? So which means that this RSA can be performed at different levels, during a project. Okay, in multiple stages it can be conducted. So first is the feasibility stage. So this kind of RSA happens, at the very beginning, right? So when the concept for the project is developed, and before the draft design of that project is made. So in between these two levels, the feasibility RSA is conducted. Okay, second is the draft design stage. So this is once the draft design has been conducted, which means it's a preliminary design. Okay, once a preliminary design for the project is ready, so if the RSA is conducted after that, so it is a preliminary or a draft design stage RSA. And the third one is a detailed design stage. So this is going one step further. Okay, once the detailed design for the project is made ready, so we conduct the RSA again. So that becomes the detailed design stage. And then we have during construction stage. So this is once the designs are finalized and the construction has started. So while the construction is going on, so the RSA can be conducted in that stage. So that is called the during construction stage. And once the construction is over, we have the pre-opening. So before the road is open to the public for use. Okay, so the pre-opening stage RSA can be conducted, and the final, the 6th level is existing road. Right, so here the road has been opened, so the public starts using it, right? So when the road is being used, so in that stage also we can conduct the RSA. So that is the existing road. Okay, so these are the different stages. So it depends on the timeline of the project, at which stage of this project is the RSA being conducted. That determines the stage for the RSA. And in each stage of RSA, different assessments or checks are done, right? For example, in the feasibility stage, what are we doing? So here we do not have access to any detailed design or anything, right? So all that we are looking for is whether the concept itself is appropriate or not, right? So whether the route choices or options that have been chosen, are they appropriate? The alignment of the roads. So these kind of things can be assessed during the feasibility stage. Then comes the preliminary or the draft design stage. Here we have from a concept level to a design level we have moved. Okay, but design will not give you all the details, right? It's only a draft design. So with that, what can we check? We can look at what is the horizontal or the vertical alignments, right? What are the cross sections? So the placement of signs and markings. So those kind of things can be assessed or checked in the preliminary stage. And once the detailed design is available, so here we can look at the geometries, right? The traffic signals, right? All these kinds of if you have intersections, the design of the intersections, all these kinds of detailed designs can be checked in the detailed design stage. And in the fourth stage, so construction has started. So when the construction is going on, so we can look at the transition zones, the warning zones, the work zones, all these things, and also the safety of the workers. and the different road uses. So that can be examined during the construction stage. Then once the construction is finished, we go for the pre-opening stage, right? So all the construction is done. So we do a final review of the construction. So here we look at the readability of the signs so that have been placed, the markings. Okay, so all the traffic control devices. So these kind of things can be done, and also how is the safety features functioning in different weather conditions and lighting conditions, right? So during day and night, during rainy weather, foggy weather. So all these different final checks can be done during the pre-opening stage, and even after the road is open for public. So during the how is the operation and maintenance of the road is going on, so that can be looked at in the final stage, which is for the existing roads, right? So here we are looking for, is there any roadside hazard that are present, right? So once again we can look at the readability of the signs, the delineators. It's all these kind of checks can be done in the existing stage. Okay, so different stage of RSA constitutes different checks. And then we have the RSA process. So RSA process, so what happens during RSA? So basically the site inspection. So RSA means we are going, it's a qualitative check, right? So we have to go to the site and then inspect the facility, right? So this has to be done both at daytime as well as at the night time, because the road will be used on different weather conditions. So we have to. Okay, so looking at the RSA process, so the site inspection needs to be conducted both at daytime as well as at the night time, and also during the different weather conditions, as I was mentioning earlier. So we have to look at first as overall how is the concept okay, like the design, and then we have to get into the details, right? So we have to pay attention to all the details, particularly at the intersections, right? So that's where the most conflicts occur. So and also we should make pay attention to all road users, right? So not just the the vehicles, but also to the non-motorized traffic like the pedestrians, the cyclists and so on. Okay, and again we have to take into consideration of all movements, right? So different traffic movements and different maneuvers, right? So we have to make sure that safety is ensured for all users, again at all weather conditions and at time of the day. Okay, so that's what we look at in the RSA process. So then we were looking at the safe system approach. So what is the safe system approach? So basically here the objective is to have zero fatalities, right? So even one death or serious injury is unacceptable, because all these fatalities on the roads are avoidable, right? So you have to take proper care. So that's why we adopt this safe system approach. Okay, And yeah, then we were looking at the different guiding principles, right? So there are 6 guiding principles in safe system approach. So one is deaths or serious injuries are unacceptable. Okay, as I said, these are avoidable. Therefore, so even one death or serious injury is not acceptable. Second one, humans make mistakes, right? So even though we have all these, rules and everything, so humans can make mistakes, right? So therefore, we need to be considerate, and the systems that we develop should be forgiving, right? So even if the users make mistake, it should not lead to a serious injury or a death, right? So system should be capable of uh, you know uh, uh, you know taking care of errors that are made and still prevent the deaths or injuries. Third is humans are vulnerable, which means that so humans are when they are exposed to high like kinetic energies. So when the crashes happen, so it can lead to deaths, right? So we must make sure the systems provide enough cushion, so that the impacts are not heavily transferred to the humans, so that it does not lead to deaths or injuries. Then responsibility is shared, which means that the responsibility for preventing injuries or deaths is not only with the drivers, right? So who is using the road, but also with all the stakeholders, right? So from the design stage, from the policy makers, right? So the construction of the project. So so everyone who is involved with the road facility, right? So whether it is in the conceptual stage, or in the construction stage, or in the operation and maintenance stage, and the user, so everyone is responsible together for achieving this zero fatalities goal. And fifth one is safety is proactive. So which means that so we have to take the measures beforehand in order to prevent the accidents, right? So we cannot wait till an accident or a death occurs to fix something, right? So we should be proactive, and fix all the issues before they manifest into this unacceptable deaths or injuries. And the final guiding principle is redundancy is critical, right? So which means that uh, which means that having multiple safety features, right? So even if one of the features fail, there is so the redundancy makes sure that there is other systems or features that are present, that make sure that accidents don't happen, right? So therefore redundancy is critical or crucial. So these are the guiding principles based on which the safe system approaches developed. Okay, and then we were looking at what are the components of a safe system approach. Okay, again, there are different components. So one is the road safety measures. So there are different ways in which we can adopt to prevent the accidents. So that comes under the road safety, sorry, not road system, road safety management. Then we have safe roads and roadsides. Okay, so this is with respect to the facility. Adopting safe speeds. Okay, so we should limit. So speed is one of the high speed is one of the major factors that leads to fatal accident. Right, so safe speeds is necessary. Okay, then safe road uses. It's not just about building roads that are safe. The user behavior is also important, right? So safe road users is also important. So this can be achieved through providing awareness and education to all the road users. Safe vehicles. The vehicle should also be safe to drive, right? So, and the final one is effective post crash care. So even if an accident happens, if the post crash care is effective, so we can prevent deaths, right? These are the different components that are present in the safe system approach. And also we looked at the implementation of the safe system approach, right? So we looked at what are the different pathways, right? So from all the different agencies and stakeholders should first commit to this approach, right? So and then we have to have effective plans, right? So from the plan and also the design, and also have a good database of this crash system from which we can learn, model, and then rectify these issues. So that all comes within the safe system implementation. Okay, so then we were looking at road safety countermeasures. So here, so these are like what are the approaches or features that we can employ to counter issues for road safety. Okay, so here, so what are the different techniques that work? How effective they are. So those were looked at in this particular lecture. So three different categories. So highly effective measures, effective measures, and not effective measures. So a number of uh, measures were introduced in this lecture and group within these categories. Okay, for example, like having good public transportation facilities, providing medians or roundabouts. So these are effective measures for combating traffic safety, and like providing separated bicycle facilities, or having signs and markings. So these are effective ways. These are not highly effective, but still these are effective ways, providing better road surface. So these such kind of measures, they are not very effective in dealing with the safety issue, right? So like that we were looking at several measures, and also two particular case studies were discussed with respect to this road safety, like having flexible poles on curves where the side distance was restricted, and the other one was having transverse bar markings that is provided near built-up area. Okay. And in the final lecture, we were looking at speed management measures. So speed management, why are we concerned with speed? Because most of the crashes, if you look at the major cause of them, it would be because of overspeeding, right? So therefore, speed, focusing on speed is very important. And also with respect to the severity of the crashes, so in the impact speed is a very important parameter, right? So higher the speed at which the impact happens, there is a higher risk of fatalities, right? So when our objective is to have zero fatalities and major injuries, the impact speed is one of the important factors. Therefore speed management is highly important. uh, okay, so then what are the different speed management measures that are available? So again, so we have different categories. So one is providing the speed zones and speed limits. Second one is engineering treatments. So these include, like, for example, traffic calming measures, like providing the speed breakers, right? Speed bumps, speed humps. So those kind of features or measures are engineering treatments. Then we have enforcement. So this is with respect to enforcing the laws, right? So making people follow the speed limits, right? So for example, having or monitoring the traffic, and providing fines for people who are violating the speed limits, right? So again, we can have like traffic cameras that are monitoring this, or we can have this variable signs board that display the speed at which people are traveling, right? So those are passive measures. Active measures are like making fines, right? So that intervenes and makes people follow or obey the traffic rules. Then we have education. So here the objective is to create awareness, and make people aware of why these measures are there, what is the significance of this overspeeding, how how major a factor it is in the accident. So these kind of educational treatments will help modify the user behavior and help reduce the or attain the safe systems. And then we are looking at some other kind of measures, like psychological measures. For example, if you have different trees around, or there is a high cognitive load for the driver, then naturally they will reduce the speed, right? So such kind of measures we're also looking at. For example, if you're having a rough surface instead of a smooth surface like a brick road or a cobble road, so in that case also people will not travel at a high speed. Okay, so these come under miscellaneous or psychological kind of measures that we can adopt. Okay, so that's all that was covered in week 12. Okay, now we can move into some of the problems related to these concepts. Okay, so the first question for this week is an accept or reject statement. So route choice of a new road alignment is done in the preliminary stage audit. Okay, we have to accept or reject. So here we are talking about the road safety audit. Okay, so we looked at 6 stages, right? The first stage is the feasibility stage. So here only the concept for the project is available, right? So we do not have any designs, right? Uh, so after the feasibility stage comes the preliminary or the draft design stage. Okay, so here we have a preliminary design. Okay, so here we are talking about the preliminary stage, which is the second stage, and route choice. Okay, so this route choice has to come up in the conceptual stage of the project, right? So before we come up with the design, we have to come up with the route choice or route options, right? So which routes we are considering. So that cannot be done uh, in the design stage. It should come before we go for a design. Okay, so route choice happens in the conceptual stage. Route choice happens in conceptual stage. Okay, so it is reviewed in the feasibility stage. Right, so because feasibility stage comes after the concept is ready, so the route choice that is available in the concept, so that is reviewed in the feasibility stage. Okay, we do not wait until the preliminary design stage. So therefore the given statement is incorrect. It is reviewed before the preliminary stage itself in the feasibility stage. So the right option is option B, reject. Okay, next question number 2. So here we are analyzing the crash history data. Okay, so we have the crash history data along with the traffic road parameters like the section length, the annual average daily traffic, number of crashes for 5 different road sections that are mentioned in the table. Okay, we have locations A, B, C, D, and E. So we know the section lengths for each of them, the AADT, number of crashes, and for how long this data has been collected for each section. Okay, so the question is, what would be the correct order of the locations in ascending order of their crash frequencies? That is crash frequency in terms of crash frequency per kilometer per year. Okay, and B is the highest value of crash rate in MVK. MVK means millions of vehicle kilometer observed among the 5 locations. Okay, so these are the 2 things that we have to find out from the given data. Okay, so first we want to get the crash frequency per kilometer per year. How do we get the crash frequency? So crash frequency per kilometer per year. So that would be the number of crashes divided by, so we want per kilometer and per year. So the section lengths are not equal to 1 kilometer, right? So we have to normalize for the number of kilometers. So divided by the section length, then you will get the number of crashes per kilometer. But we also want per year, right? So the data, the number of crashes that is given in the table is not for 1 year. It's for for a different number of years. So we have to normalize for the time as well. So multiply by the study period. Okay, that will give you the crash frequency per year. Okay, so we have the locations. So A, B, C, D, E. So crash frequency. So for location A, what would be the crash frequency? So it would be 8 crashes divided by section length is 1.9 kilometers into study year is 2.75 years, right? So if we calculate that, 8 by 1.9 into 2.75, so that is equal to 1.53. Okay, so that is the crash frequency for site A. Okay, similarly we have to calculate it for the other sites as well. For site B, it will be 2 crashes in 0.4 kilometers over 4.5 years. Okay, so 2 by 0.4 into 4.5, that is 1.11 crashes per year per kilometer. Okay, for site C, so this is for A, this is for B, 13 crashes over 7.2 kilometers in 0.6 years. So 13 by 7.2 into 0.6, that is 3.01. Then for site D, it is 17 crashes in 2.9 kilometers over 3 years. 17 by 2.9 into 3, that is 1.95 crashes per kilometer per year. And finally for site E, it is 6 crashes in 3.4 kilometers over 1.65 years. So 6 by 3.4 into 1.65, that is 1.07. So D equals 1.95. So we obtained the crash frequency for all the sites. The question was to order them in ascending order of the crash frequency. Okay, so the smallest crash frequency is for site E. Okay, followed by site B 1.11, then it is site A 1.53, then site D, finally site C with 3.01. Okay, so it is E, B, A, D, C. That is the correct order for the crash frequencies. Okay, so then the second part is to find the crash rate, right? So and then obtain the highest value of the crash rate. Okay, so how do we get crash rate? Okay, so for crash rate, what we have to do? Take the number of crashes. Okay, so divide this by the AADT, multiply AADT with the section length. Right, so AADT multiplied by the section length will give you the total vehicle kilometers travel, right? So this is the number of vehicles so in a given day, right? So but we want for a given year, so over a given year, so we have to multiply it by 365 because AADT means what? Annual average daily traffic, right? So it's for 1 day. So for a year we have to multiply it by 365. That gives you the total number of vehicles using that section in a year, and then multiply it by the section length. That will give you the total vehicle kilometers traveled, and then we have to also normalize it by the number of years, right? Because the study period is more or less than 1 year, so we have to normalize for that. So and also we are looking at in terms of million vehicles, right? So we have to divide this by 1 million, so that can be taken to the numerator. So multiply 1 million, right? So this is just for the units, right? So because you want it in millions of vehicle kilometers travel. Okay, so this will give you the crash rate. Okay, so crash rate for site A will be what? So number of crashes is 8 divided by 3500 into section length is 1.9 into 365 into study period is 2.75. So how much that will be? So again, you have to multiply it by 1 million, right? So 10 power 6. So 8 into 1 million divided by 3500 into 1.9 into 365 into 2.75. That is 1.20, okay, million vehicles kilometer, right? Crashes per million vehicle kilometers. So this is 1.2 for site A. Then for site B, it will be 2 million by AADD is 1400 into section length is 400 meters, 365 into study period is 4.5 years. Okay, so that would be 2 into 10 power 6 divided by 1400 into zero point 0.4 into 365 into 4.5, that is 2.17. Okay, so next we erase this part. Okay, for site C, number of crashes is 13. So by 6300, say ADT, 7.2 kilometers, 365 into 0.6, 50 power 6 in the numerator. Okay, so 13 into 10 power 6 by 6300 into 7.2 into 365 into 0.6, so that is 1.31. Okay, for site D, 17 crashes, 5200 vehicles per day, 2.9 kilometers, 365 days, 3 years, so millions of vehicles. So 17 into 10 power 6 divided by 5200 into 2.9 into 365 into 3, that is 1.03. Okay, 1.03. And finally for site E, it is 6 crashes into 10 power 6, 900 vehicles to 3.4 kilometers, 365 days, 1.65 kilometers. So that will be 6 million by 900 into 3.4 into 365 into 1.65, that is 3.26. Okay, so we have calculated the crash rate for all the sites. Okay, what is the question? The question is, which site has the highest value of the crash rate? So among the 5 sites, so it is site E which has the highest value of 3.26. Okay, so the highest value is 3.26 crashes per million vehicle kilometers travel. Okay, so that's how we analyze this crash data. Okay, so those are the answers for question A. In ascending order, the crash frequencies is for site E, followed by B, A, D, and C. And for the second part, the highest value of the crash rate is 3.26. crashes per million vehicle kilometers. Okay. So moving on to question number 3. We are given 4 statements and the question is to find which of these statements are incorrect. Okay, the first statement is identification of black spots is a compulsory task to be exercised before conducting the road safety audit. Option B is traffic density influences driver's speed choice. C, active intelligent speed adaptation systems advise the driver and display visual audio cues to alert drivers while overspeeding. D is detailed design of the intersections is checked during the pre-opening stage of the RSA. Okay, so here we will look at each of these statements individually. So first statement says identification of black spots is compulsory to be exercised during the conduction before conducting RSA. So this is an incorrect statement, right? So black spot, what are black spots? So these are locations with a high potential for accidents, right? So where these are the stretches of road where accidents occur at a high frequency, right? So these black spot identification is not really a compulsory task for RSA because RSA is not on, it's not concerned only about these black spot locations, right? So RSA is conducted for the entirety of the road system, right? So we want to identify and all potential issues for safety, right, and eliminate them, right? So therefore, we have to focus on all the locations. So identifying black spots is not really a mandatory task for RSA, right? So this black spot identification we do when we are doing, investigation, crash investigation, right? So there, black spot identification are used, but for RSA it is not compulsory to do that. So B, traffic density influences driver's speed choice. So this is true. So speed depends on the traffic density, right? So when you have a very low density, right? So close to zero, so the driver can travel at their desired speed, right? So they can travel at a higher speed. But as the traffic density keeps on increasing, right? So the driver's speed choice will also come down, right? So because the freedom to move flexibly comes down, so therefore the drivers will adopt a lesser speed. Okay, so density influences the traffic speed, right? So at higher congestion you will have lesser speed. So B is a correct statement. C, active intelligent speed adaptation systems advise the driver and display the audio visual cues to alert the driver while speeding. This is incorrect. Right, so these kind of systems like advising and displaying audio visual cues, so these are called passive intelligent speed adaptation systems because these are not these kind of measures do not intervene and make the driver reduce the speed, right? So even though we are providing this advice and the visual audio cues, the driver may simply choose to ignore them, and continue to travel at the current speed, right? So it is possible. So these are only passive measures, right? So we are not actively intervening to make the driver reduce the speed, right? So we are only advising the driver. The driver has to make the effort to reduce the speed. So therefore, these kind of measures are called passive measures, right? So and therefore not active. So C is an incorrect statement. And D is detailed design of intersections is checked during the pre-opening stage of the RSA. So this is also incorrect. Okay. So pre-opening stage is the second last stage, right? So where the construction is done, right? After the construction is done is where the pre-opening stage RSA is conducted. Right. So that case we will not be checking the design. Detailed design checking should happen much before, right? So even before the construction starts, the design has to be verified, right? So therefore it happens during the design stage, during the detailed design stage. So that's where the detailed design of the intersections are checked. Okay, therefore the incorrect statements are A, C, and D. Okay, question number 4, we have to match the items given in column X with the corresponding items given in column Y. Okay, so in column X, we have injury minimization criteria, education and enforcement, detailed design of junctions, effective road safety countermeasure. In column Y, we have construction stage RSA, gateway treatments, school-based education and training, design stage RSA, speed management measure, and setting of speed limit. Okay, So first one is injury minimization criteria. So that is, this criteria is used for setting of the speed limits. Okay, so depending on to reduce the injury, right? So depending on who is using the road, right? So whether vulnerable road users are present, right? So whether access restrictions are there or not. So depending on such information, to the criteria is to reduce the injury, right? And this criteria is used for setting the speed limit, right? So speed limit is adopted based on this criteria so that the injury is reduced. Second, education and enforcement. So or where do we use education and enforcement? So education and enforcement is used for as a speed management measure. So there are multiple measures for managing speed, right? So we looked at different categories. So providing education and enforcement are also two of the categories that are under which the speed management measures can be classified. The third, detailed design of junctions. So where do we use the detailed design of junctions and intersections? So that is reviewed in the design stage of the RSA, right? So as we saw in the previous question. And finally, effective road safety countermeasure. So out of the remaining three, A, B, and C, the road safety countermeasure which is effective is B, gateway treatment. So what is gateway treatment? So gateway treatment is basically so when you have two different facilities of varying speed limits that are merging or intersecting. So in that in such environment, so this great gateway treatments are like providing signs and other facilities such that the this intersection or merging of this two environments, road environments, is taken care of in a proper way, right? So that's what we call as the gateway, right? So it is the gateway between two different road facilities, right? So one is of say higher speed, the other one is of a lower speed. Okay, so those kind of treatments are effective for ensuring the safety. So the right matches, one is matched with F, 2 is matched with E, 3D, and then 4B. So that is given in option B, right? So the right answer is option B. Okay, then question number 5. Which of the following statements is incorrect? So option A is ordered data models can be used to develop crash severity models. Option B, roundabouts are very effective in reducing speed of vehicles. C, safe system approach does not focus on awareness and education. And D is none of these. Okay, first one, ordered data models can be used to develop crash severity models. This is true. Okay, we are looking at crash severity data. Okay, crash severity data is qualitative, right? So it's an ordered categorical variable, right? So there, ordered data models are suitable, right? So count data, if you are looking at like crash frequencies, there the Poisson or the negative binomial regressions are used. But for crash severity, the ordered data models are suitable. So option A is correct. Option B, roundabouts are very effective in reducing speed of vehicles. This is also true. So in roundabouts, so when you have multiple legs intersecting, so roundabouts is an effective way of protecting that intersection, right, by reducing speed. It's also very efficient in terms of handling a large volume of traffic as well, right? So roundabouts are very effective measures. Um, C is safe system approach does not focus on awareness and education. So this is an incorrect statement. So why? Because safe system approach does focus on awareness and education. So if we recall the different components that are present in the safe system approach, so one of the component is safe road users, right? So how do we ensure that the road users we have safe road users? So by focusing on awareness and education, right? So through that we will achieve safe road users. So that is part of the safe system approach. So C is incorrect statement. And because C is incorrect, so D, none of these is not applicable. Okay, so we can leave it. So the right answer is option C, that safe system approach does not focus on awareness and education. Okay, question 6 is which of the following are incorrect regarding safe system approach? Options are human errors are inevitable, saving lives is expensive, fatalities due to road traffic crashes are inevitable, only drivers, that is offenders, are liable for road traffic fatalities. So option A, human errors are inevitable. That is true, right? So we have seen that humans do make mistakes, right? So that is one of the guiding principles for the safe system approach. So saving lives is expensive. So this is not correct. So we have a number of saving lives is not expensive. So we have a very effective yet cost efficient measures, countermeasures that can be adopted for improving the safety, right? So saving lives is not an expensive task. And C is fatalities due to road crashes are inevitable. No, road crashes are completely preventable, right? So that's why we have zero road crashes as the goal in our safe system approach, right? So because all these crashes are totally preventable. And D, only offenders are liable for road traffic fatalities. No, according to safe system approach, responsibility is shared, right? So all the stakeholders should be responsible, collectively responsible for achieving the zero traffic crashes, right? So therefore, we cannot just hold the drivers as accountable. Okay, so B, C, and D are the incorrect options. Therefore, the right answer is B, C, and D. Okay, question 7 is, which of the following are incorrect? Options are, relocation of road safety hazards is more effective intervention than eliminating it. Option B is, speed has an impact on the likelihood of a crash but does not have an impact on the severity level of the injured person. Option C is, road signs and markings help in reducing the number of road crash fatalities effectively. And D, presence of trees or overgrowth on the roadside increase confidence of drivers to drive at higher speeds. Okay, option A is, relocation of safety hazards is more effective intervention than eliminating it. So this is incorrect. So completely eliminating the hazard is the more effective way, right? So relocation, if you relocate it, it's going to be causing it's going to reduce the hazard at the location from which it is moved, but wherever you are keeping it, so in that location is going to create issues, right? So completely eliminating it is the best option. Okay, so that's more effective. So given statement is incorrect. So B is, speed has an impact on the likelihood of the crash, but does not have an impact on the severity level of the injured person. So this is also incorrect because speed has an impact on both the likelihood of a crash as well as the severity, right? So higher speed will increase the probability of an accident or a crash. It will also increase the probability of a severe injury, right? So it also increases the likelihood of the fatalities. Okay, so B is incorrect. C, road signs and markings helps in reducing number of crash fatalities effectively. This is true. So road signs and markings are one of the effective measures to bring down the road crashes. And D is, the presence of trees or overgrowth on the roadside increases the confidence of drivers to drive at higher speed. So this is incorrect. So why? Because so they actually do the opposite. The presence of trees and overgrowth will increase the cognitive burden for the drivers, right? So this is one of the psychological measures that we were talking about. So if you have these trees and other overgrowth, so that will create friction, and therefore the drivers will not travel at higher speed, right? So they are more likely to travel at a lower speed. So the only correct statement is C. So the incorrect ones are A, B, and D. Okay, question number 8 is, accept or reject the given statement. Statement is, length of the transition zones depends on width of the carriageway. Okay, so this is an incorrect statement, so we reject it. So why? Because the length of the transition zone does not depend on the width of the carriageway. It depends on the speed limit, posted speed limit. So where do we give this transition zone? So when the when you have two sections, so where the speed limits are varying widely, right? So for example, you have a 40 kilometer per hour speed limit section meeting a section with 80 kilometers per hour, right? So in this case, in this case there is a huge difference, right, between the two sections. So to prepare the drivers for this abrupt change in the speed limit, so we provide a section which has an intermediate speed limit. Okay. So for example, between 40 and 80, we can have a section, introduce a section that has a speed limit of 60. Okay. So therefore, the drivers will be much more prepared for this change in the speed limits. Okay, and how long this speed limit should be? So that depends on the how long should this transition zone should be dependent based on the the speed limit, right? So if you're traveling at higher speed, right? So and if you have to suddenly change into a lower speed, so you have to give a longer transition zone so that the drivers can appropriately slow down and then come into this lower speed limit zone, right? So the speed limit determines what should be the length of the transition zone and not the width of the carriageway. Okay. So width of the carriageway can determine the speed limit, but it's not directly going to affect the transition zone. Okay. So therefore the given statement is rejected. And then question number 9 is which of the followings are correct? Okay. So we have to choose the correct ones. Options are drivers reduce speed with decrease in cognitive burden. B. Enforcement related speed management treatments include road safety campaigns. C. Speed narrows down the vision of a driver. D. With increase in speeds, travel time, costs for fuel consumption, pollutants, and road crashes are reduced. E. Speed limit transition zones are required when the road function transitions. Okay. So, first statement A. Drivers reduce speed with decrease in cognitive burden. So, this is incorrect. So, it's the opposite, right? So, what we saw in the previous questions. So, drivers will reduce the speed with increase in the cognitive burden. So they have to look at multiple things and react to multiple things that are happening. So the cognitive load will increase. In that case, they will not travel at a higher speed. They will reduce the speed so that they can manage all those things, right? So drivers will reduce speed when the cognitive burden is higher. B. Enforcement related speed management treatments include road safety campaigns. So this is false. So these road safety campaigns are not part of the enforcement related measures. These are education related measures. Okay. So we are trying to educate the drivers and the road users. So this does not come under enforcement. C is speed narrows down the vision of a driver. So this is the correct statement. So if you travel at higher speed, your cone of vision will become narrower, right? So you will not be able to see, have a wider field of vision, right? So that's also one of the reasons why higher speeds will increase the likelihood of crashes, right? Because you are not fully aware of your surrounding. You have a very narrow field of vision. D, with the increase in speeds, travel time, cost for fuel consumption, pollutants, and road crashes are reduced. So this is an incorrect statement. So here, this is the factor, right? Higher speed, and we are looking at the effect of that. So travel time will surely reduce, right? So when you're traveling at higher speed, your travel time is going to come down, but your cost, the pollutants that are emitted and road crashes, they are not going to reduce, it will only increase. So therefore the given statement is incorrect. And finally, we have speed limit transition zones are required when the road function transitions. So this is also correct, right? So this is again what we saw in the previous question. So when we have road function is transitioning, so the speed limits may be different. Okay. So in that case, you have to provide this transition zone so that the drivers will be better prepared for this change in the speeds. Okay. So the right statements are C and E. Okay. Question number 10. You have to mark the incorrect statements. Option A, roadside barriers are very effective in reducing the number of crashes and fatalities. B, as per MORTH, maximum permissible speed limit in urban areas is lower than that in rural areas. C, filling of checklists is a compulsory task to be exercised in RSA. And D, traffic humps and chicanes are not very effective as speed calming measures. Okay, so option A, statement A, roadside barriers are very effective in reducing the number of crashes and fatalities. So that is a correct statement, right? So this will help in reducing the crash severity and also the number of crashes. So option A is correct. Option B is as per MORTH, the maximum permissible speed limit in urban areas is lower than that in rural areas. So this is also true, because in rural areas, maximum permissible speed limit will be in the range of like 100 to 120 kmph, whereas in urban areas it will be like maximum 70 kmph. Okay, so therefore for urban areas it is lower than in rural areas. So this statement is correct. C. Filling of checklist is a compulsory task to be exercised in RSA. So this is incorrect. So while we have a checklist, but filling that is it's only there so that the auditors do not miss anything while they are doing the auditing, right? So that only it's only there so that the auditors don't miss anything, but it's not a compulsory task. It's not a part of a compulsory task as a part of the RSA. And D, traffic humps and chicanes are not very effective as speed calming measures. This is also incorrect, because these traffic humps and chicanes, they are very effective speed calming measures, right? So they work very well. So the given statement is not correct. So the only incorrect options are options C and D. So that's the right answer. Okay, then we have question number 11. Accept or reject the given statement. For ML-based crash data modeling with labeled data, unsupervised learning algorithms are generally used. Okay, so here what are we looking at? So when we looked at crash data modeling, so we had two major approaches, right? So one was statistical, another one is machine learning. Okay, so under statistical, again we had models for count data and models for crash severity, which is ordered data. Under ML we had three major classifications. One is supervised, semi-supervised, and unsupervised. Okay, so how these three methods vary, it's based on what kind of data that we have. Okay, for supervised, we have all labeled data, right? So in that case, supervised learning is more suitable. So for semi-supervised, we have some labeled data and lots of unlabeled data. And for unsupervised, we have all unlabeled data. Okay, so that's the choice of the ML method will be dependent on what kind of data that we have. Okay, so here we are talking about ML based crash data modeling with labeled data. And for this, the statement says unsupervised learning algorithms are generally used, right? So if you look at it, so we are using all labeled data. Okay, for this, which is more suitable, it is supervised learning. Okay, so the given statement is therefore incorrect, right? Because for unsupervised learning is more suitable when we have all unlabeled data, but we have all labeled data. So in that case, we should go for supervised learning. Okay, so therefore we reject the given statement. So the right answer is option B. Okay, so with that we are coming to the end of today's session. Okay, and we are also completing all the 12 weeks. Okay, so with this all the concepts related to the traffic engineering course have been covered. Okay, so but we will have one more extra session, right? So which is tomorrow. Okay, in that session it will be happening in the same time window from 4 p.m. to 6 p.m. and where we will be trying to cover all the contents, right? So in all the 12 weeks, so we'll try to summarize what has been taught throughout this course. Okay, so we'll try to provide a quick recap, right? So of all the things. So if you have any doubts, you can join and then ask, right, from any of the weeks. Okay, so we'll do some problems from all the different weeks that we have covered so far. Okay, so that will be like a summary session that will help you with your exams. Okay, so with that, we'll close today's session and meet again tomorrow. Okay, so thank you all for attending.